Okay, here we are, y'all. I'm going to be recording this lecture today, and we are on Module 1, Part 1, right?
Yep.
Because we didn't start anything. Did y'all start reading your module?
Yeah.
Yeah? Okay. I think in your book maybe it shows, how to keep up on your reading, right? In those little check boxes or whatever. So we're looking here. Hold on. All right, so keeping up, right, you have that box where you can put the checks in the boxes over there so you can make sure that you're going to get everything read on time. But remember, it doesn't matter to me when you read it, as long as you read it in time for the quiz. All right, so we'll have Part A this week. Next week we'll finish up Module 1, and then the week after that we'll have our first quiz in this class. All right, so I guess last time we didn't really get into any of the actual module, right? We just talked about generalities about science. All right. So the basics of physical science then, which is what our course is, and y'all know I'm a life science. That's my specialty. None of that's in physical science, okay? So we'll be studying things that are not life science. So what we are studying God's creation, however. That's your first blank. I have it underlined. So you should have the words science is studying, and you have a blank there, and in the blank you're going to say God's creation. All right, so we could say that about every science course that we ever take, right? Y'all could even say that about your English and math courses, that you're learning about God's creation there. I think so. Math is really, God invented that, and that's why math works the same way every time. 2 + 2 is always 4, right? So that's pretty cool.
I thought 2 + 2 was 22.
Not 2 + 2. Science and technology work together to help people. That's your blank. You're filling in the word help. All right, so science is a helpful tool for understanding God's creation better. On the left there it says God's creation. He created it and said it was very good, right? So we know that God created everything. He said it was good. Then things went a little sideways, right, when there was some disobedience in the world. And now we have problems in the world, namely that we have things falling apart and dying, right? And that's part of the fall. And that's okay because he's redeemed us, right? He's redeemed the broken parts and made us whole again. Natural science is divided into 3 general categories. So notice it's called natural science. Okay, so my degree from the University of Texas, microbiology, was in the natural sciences department. And so that's because there might be other, like for instance, there's something called political science when you're studying politics, right? It's a different kind. Natural science when you're discovering and looking at the world and the natural things in the world. All right, so here are the 3 branches. I think you're going to write these down. Life sciences, physical sciences, and earth sciences. Is that the part you're writing, or are you writing what things belong in each one of those?
No.
Okay, so like for instance, in life sciences you have botany. That's the study of plants. You have genetics. That's the study of DNA and the distribution of genetic traits, and also the production of proteins in the body, things like this. Ecology is the study of nature and taking care of it, kind of like green science. Zoology would be the study of animals. And it is pronounced zoology, by the way, not zoology. Human biology, that would just be, we could have written just biology there. Biology, the study of living things. Human biology would be the study of the human body, which I teach that course too to seniors. Senior level, it's called Anatomy and Physiology, or A&P, and it's a tough class. If you want to be a nurse or a doctor or a physical therapist or something like that, A&P is a good course to take. Physical sciences include physics, chemistry, astronomy, and of course this course, which is known as physical science, right? Sort of like physics, motion, and things like this. Yes, Josh?
So as in astronomy, in space, we learn about more like black holes or stuff?
Sure, we learn about different things in space, planets and stars and stuff like this. I can't remember in this class if we spend much time on that. But we should. Yeah, I know we're definitely talking about chemistry in this class, which is new. We didn't used to do that. Just remember, this course is brand new. This is the first time I'm teaching from this particular book. Yeah. Earth sciences, we're covering some of this. I believe in this, right? We have geology, study of rocks and soil and things. Oceanography. Oceanography is the study of the ocean, but not the life in the ocean, okay? Like the salty water, the geology of the ocean floor. You know how we have mountains and and valleys and stuff on the top of the earth. We also have mountains and valleys under the ocean as well. Meteorology would be the study of space stuff that enters into our atmosphere, so we can study space rocks and like meteorites and things like that. It's also the study of weather, you know, the weather and how weather changes. And then paleontology is the study of fossils, past life that has died. Yes?
Mr. Benoit has a degree in geology or meteorology.
That's correct. So Mr. Benoit is a weatherman, basically. Yeah, I think he did weather tracking and stuff. I don't know that he was ever on TV as the weatherman in front of. I don't know. He may have been. Y'all should ask him that. I just know that he definitely was the weatherman, but I think he was just doing the data research. But I could be wrong. All right, are we good? Do we have a few things written down under these 3 branches of science? Yes, very general stuff here, huh? The branches of natural science. Okay, so physical science is the study of non-living things, whereas biology is the study of living things. Physical science is the study of non-living things, using the scientific process called the scientific method. And those of you who were in general science last year, we spent quite a bit of time on the scientific method. All right, so we'll have a little redundancy here on that, a little repetition. You'll see some stuff you learned last time that we will have to know again. And that's because it is very important. Scientific method is integral to understanding the way that we run science. Remember how we talked last time about science doesn't prove anything? Right? The only way we can show, science can help us to show something to possibly be true or valid is if it goes through the process called the scientific method. All right, so we have steps for this, and I'm going to put them up one at a time because you have to write them down. I think you have a blank, right? And you have to write the whole thing down, okay, because you need to know it. Number 1, make observations. Essentially what number 1 is talking about is you're going to wonder about something. You're going to ask a question. Why is the sky blue? Why do grasshoppers jump? You can ask a question about anything, all right? And we can probably apply scientific method to it to try to understand it. For instance, in general science, we talked about a guy who said, I wonder if there's any life on Mars. Remember that guy? Percival Lowell? Yeah, Percival Lowell. Well, I think we're going to talk about him some more this year. And how he did some things to try to answer the question, is there life on Mars? Okay, and so most of it had to do with observing, right? Looking at it through a telescope, because we haven't been able to get to Mars. Recently, we've been up there with a little machine, you know, but that's it. We're trying to get to Mars. Number 2, we're going to conduct a little background research. I've got a question. I'm going to look up some stuff that other people have answered about that particular question. If I'm looking at, you know, grasshoppers, I'm going to look up some stuff about how does a grasshopper's anatomy look like. What do they, that shows how they jump. Why do they jump? That kind of thing. Yes?
This part of it wasn't in the scientific method, but in general science.
Right. In fact, I will say there were several things that were changed. And furthermore, I think when we talk about, I think in my biology class when I talk about the criteria for life, it's way different than what it said in general science. So I'm like, whoa, we had 4 things, and now we have like 6 things or something. Yeah, so, because the next thing's going to say I'm going to form a hypothesis, which probably was the second thing in general science. Form a hypothesis is a way to answer my question. So I have a question, and then I'm going to try to answer it by saying, I think grasshoppers jump because whatever I come up with. And then I'm going to conduct, I'm going to design repeatable experiments and then conduct them to test the hypothesis. So remember, our observation is the question, our hypothesis is I think. It usually starts with the words I think this will happen, or this is why, or whatever. And then we design a repeatable experiment, and not just repeatable by me, but other people. I have to write it down so clearly. It's as if you took your general science book from last year and opened it up and read one of your lab pages, and you know exactly what you did, and somebody else who didn't even know you could read it and repeat that. And probably you didn't write that good of a lab write-up because it's kind of hard to put all that background information in there. But the idea is that a colleague somewhere in another part of the world could look at your paper and repeat exactly what you did because your notes were so good on how you conducted your research. Collect and analyze the data and draw conclusions from that. All right, and then determine if your hypothesis was correct or you need more testing. And keep in mind, some people write a hypothesis, they pose a hypothesis that they're hoping is wrong. All right, so in other words, they'll say the opposite thing. They'll try to disprove their hypothesis. And that's just as valid. You can do that as well if you like. Remember last time when we had our little film canisters that popped up, right? And some of us had guessed that they would do that. Some of us hadn't guessed that they would do that, whatever. That was our hypothesis. I think that it'll pop up, kind of a thing. You could have said something that you knew wasn't going to happen. I think it's going to turn purple, right? And just to show your hypothesis was wrong. That's a valid way of testing something, to show that you're wrong. It's okay to be wrong in science. In fact, science is all about being wrong and disproving things. We can disprove things all day long. Just can't prove anything. All right? Observations. An observation would be gathering information using our senses or using some sort of instruments. Okay, some sort of measuring instruments. In fact, do y'all have rulers with you in your backpacks today? Does anybody have a ruler?
No.
Nobody has a ruler? I
Oh,
forgot
I
to
do.
bring mine. You do?
I need
Okay.
to bring one tomorrow though. Just
I need-
I have we might need it during lab time. I have a tape measure. That's the closest I come up to a ruler because I meant to. I have several like small ones that'll fit in my pencil box, you know, like 6-inch rulers.
Yeah, it's meant to be
And I
centimeters.
forgot them, so I don't have them. So, but that would be an instrument that we could use. In biology, one of the instruments I'll be using today in my biology class will be using a microscope. Okay, so that's a way of looking at, observing things a little more closely, right? It's still observing, but an instrument is helping me to aid my senses. Like this guy's using a magnifying glass right there. All right, so two ways to make these observations. One is called qualitative. All right, I think you have a blank for this one, yes? Qualitative. So qualitative, you see the word quality in there, okay? So that would be observation using my 5 senses. I'm looking at something and I'm gathering information from my senses. If you're in a cooking class, some of that sense could involve taste, right? You could be tasting something, be smelling something. Mostly in science, it'll be our vision. We'll be looking at something. Possibly listening if it's making some sort of noise, you know, a chemical reaction or something. And then we have quantitative. You see the word quantity in there. And we make observations using instruments like rulers, balances, which is a scale. We'll be using a scale today. Beakers, microscopes, things like that. Those are the tools that we would use for a quantitative observation. It's still using senses, but senses being aided by something. All right, so I found this, and this comes right out of your book. It's a picture here that we're looking at African animals near a watering hole, okay? What quantitative and qualitative observations can we make about what's happening in this photo?
They're all looking at the lion.
Well, they're all doing what?
They're all looking at the lion.
Looking, well, I would be too.
They're
What's that
after you,
lion
okay.
doing there? Yes, John Mark.
The actual species are more closer to each other than to other species.
It's, yeah, like the giraffes are grouped together, the water buffalo, I guess, are grouped together, and these little elk or whatever, pronghorn
Gazelle.
antelope or gazelles or whatever. I think they might be the most nervous when they see this guy just strolling through. Where do you think he's going?
The water hole.
To the watering hole.
I
Okay,
think my
that's
dog
probably
came
where
out
he's
from
going. And
outside.
how do we know that? Because it told us down here, African animals near a water hole. That's the only reason we know that, right? If we didn't know that information, we had no idea where he's going. Maybe he just finished eating one of these guys and he's not hungry, and so therefore, you know, nobody's worried because he's full. You know, something like that.
Yeah, that's
So
cool.
those are our quantitative, right? So no, is that right? Those are our qualitative. To write those down. What kind of quantitative? I don't know. Can we make any quantitative observations? How do we measure something with this? How? Yeah. What can we do?
The words they gave us about the water hole, that was quantitative.
You think that's using that information? So that's extra than just my. I like that. I think that's a good point. So that could be our quantitative, right? Okay. And there's another creature. Is that another one of those water buffalo? Maybe it looks. Is that an ostrich or something?
Yeah.
That's an ostrich.
Right there.
Weird. Okay. All right, so those are the kind of things we're making these. We're gonna hone this down even more to say some things that we can observe and some things we're assuming. We're making an assumption on some things. Okay. At the end of an experiment, at the end of experimentation, a series of experiments, the hypothesis is either supported or not supported. Either I can say my hypothesis was incorrect, or my hypothesis was correct. If it was incorrect, I think a better experiment might center around doing this change, making some sort of change. And remember, sometimes we want it to not be supported on purpose. On purpose, we'll say, okay, yeah, like I thought. I'm wrong about that. All right, so we can check our work that way then. If our hypothesis is supported, then we can say that our data does seem to support the hypothesis we made. But remember, we can never 100% say that this is absolutely true all the time. All right, designing experiments involves choosing factors to test. Your first blank is the word factors. All right, in a controlled experiment, the factors that influence the outcome are kept the same, except for something being studied that we called a variable. We're going to change one thing. All right, we'll change one thing and see what that variable will do. For instance, if I were growing some plants and I wanted to test different fertilizers, I would have the same kind of plant in the same kind of pot, the same age, sitting in the same window, so all of that would be the same. The only thing that would be different would be the fertilizer, right? I'd probably have one that had no fertilizer. Then I would have one with the expensive fertilizer. Then I would have one that we're using just compost or something. And then I would have one that we're using, I don't know, cheap fertilizer or whatever, something. And it would, whatever choice we make. And then we're going to see how the plants respond. Do they grow better or whatever? But we can't, like, put one of them in a closet. Okay, because is the plant going to do well in a closet?
No.
No, because it needs sun, right? So they all have to have the sun. Now, if I were testing that, how much light does a plant need, I would have one in the full sun, I'd have one in shady area, I'd have one in a closet, right? And I would see how important it was for plants to have sun. Do you see? The variable there would be the sun exposure. But the fertilizer one would be the fertilizer exposure. Yes?
Yeah, watch out for the plant, but get your clothes out.
Yes, that's true. You put it in a closet, maybe you don't use very often. Doesn't let a lot of light in there, Next, a variable is a factor that changes in an experiment. We all know this from general science. That's the thing that changes. I want everybody to remember that. Good quiz question, by the way. A factor that changes in the experiment. All right, so this is what I'm telling you. Sometimes our observations are based on something besides strictly observations. Sometimes we're making some assumptions. So an inference is a logical conclusion drawn from the observations that we made, also drawn from previous knowledge and available information often used by scientists when direct observation is not possible. Like we were looking at that picture at the watering hole, for instance. We weren't in Africa, all right, so we had a photograph to look at. That was nice. And some of the inference were being, like one of my inferences was maybe the lion was not hungry because he wasn't attacking the animals, right? But I don't know that for sure, do I?
Unless he did after that picture.
Unless I what?
Unless he did after that picture.
Unless I did what to the picture?
Unless he attacked after the picture.
Oh, right. So if I knew more information, for instance, I could make that determination. Yes, John Mark.
If a lion wanted to hunt a prey, it would have to be more stealthy to actually hunt the prey, because you can tell its posture and speed on how it will attack you. Like,
yeah, he didn't seem aggressive, right? He didn't have an aggressive posture. I like the way you use that word there. Say again?
He was just strolling,
Yeah, right. Like he didn't really care about all those creatures there. Okay, so like for instance, we could say here an observation over here on the right. Observation: a plant is wilted. We can see that, right? If a plant is wilted, but we could infer that the plant was wilted because it didn't have water, right? That's a good idea. Why is it wilted? Because it didn't have water. Here, the second one, the car stopped running. So we might infer the car stopped running because it's out of gas. But we don't know that. It's just an inference that we're making. Okay, so this is just the difference between observation and inferences. Okay, we're going to compare those two. So we have a little video here to watch.
When you observe in science, you use your 5 senses to notice what's occurring. You could be watching and listening to a squirrel dig for its cached food, feeling the bottom of a test tube to see if it's warm or cold, or getting a whiff of the embalming fluid before a dissection. But sometimes we think we're making an observation when we're actually making an inference. You have life experiences and background knowledge that helps you to make sense of the world around you. Sometimes you make assumptions or hypothesize, but it's important that you can support your inferences with your observations. Let's look at a scenario where we can make observations and inferences. Look at this picture. There are definitely visual observations that we can make. This looks like a tire and it's flat. There also appears to be rust and sand beneath the tire. Those all fall under the category of observations. Now I'll state some inferences that I've made about this picture. Based on the sand, I think this might be in the desert, which makes me also think that it's very hot there. I think it's part of a very old truck because of the way the wheel well looks. And I'd also infer that the tire is not fixable because of the white threads that I can see on the edge of the tire. Those are all inferences. When you make inferences, be sure that your observations can back up your inferences. If new observations come in that don't fit your previous inference, it's time to revise your ideas. Thanks for watching this episode of Teacher's Pet.
All right, so we get that. So here we go, examples of inference. Observation, the flower in the doorway, the floor in the doorway of class is wet. So you walk in, there's a wet spot on the floor right here. Possible inference, there might be a leak from the ceiling, right? A leak in the roof. Somebody spilled water, or the janitor is fixing to scrub the floor, right? Those are inferences, okay? These are all possible explanations as to why the floor might be wet. We know that ceilings sometimes leak, people sometimes spill water, and water and soap are used to scrub floors. Okay, so you could have guessed one of those things.
Maybe it's
Other
flooding.
things.
Could have been, could have come from beneath or something like that. You got another one there?
I said that there could be more.
Oh, sure, there could be other ones, sure. I had ice in here earlier. I could have dropped an ice cube and it melted, right? I had some ice for my chemistry class. All right, so here we go. Observation versus inference. Okay, so take a look at this picture. It took me a while actually to figure this one out. I'm going, what is going on here? Okay, so what can we observe? Let's talk about observations first. We're in a laundry room, right? Looks like a laundry room. Yes, Josh.
Looks like the dog's hiding.
There's a dog hiding back here.
The cat's looking for something in the laundry.
Yeah, cat's peering into the dryer or washer or something. I'm guessing that's the dryer. Front loader right there. Okay, so those are some observations. What inferences can we make?
It's in a house.
The dog wants the cat to go in the thing.
Yeah, so
Wants to
Trying to
shut
commit a
it.
murder or something? Like
so what this says, y'all, is food. F-U-D spells food. That's a dog's way of spelling food. I kept saying, what is FUD? What is cat bud? You know, so food. So cat food, cat food, cat food. Okay, so this is interesting as far as inference goes. Who wrote that?
What is the dog saying?
The dog.
The dog is saying, oh please, oh please. Please, please, please. Like,
Is he
believe
trying to get
that
to go
there's-
in there?
The dog's trying to trick the cat.
What now?
The dog's trying to trick the cat.
The dog's trying to trick the cat into
Dog's
getting
like,
into the
"Yeah,
dryer,
And then he's gonna turn it on.
and he'll turn it on and
That's a
that
smart
kind
dog.
of thing. Yeah.
That's a smart dog.
So we can infer that the dog doesn't like the cat very much.
Yeah.
We also can wonder about the wisdom or the knowledge that the cat possesses. Is it reading those words? Cat food?
The dog wrote with a little marker.
Is there actual cat food in the dryer?
There's a box up there.
on the thing.
Or
Is
is that-
that? I can't tell what that
or is
box
that
says. That
detergent?
could be laundry detergent, as far as I can tell.
Can you read it?
No, can't read it.
That's the point, not to read it.
Okay, yeah. All right, but you see how we have some observations. Now, see, something came out of that cabinet. Why is that cabinet door open?
Oh yeah.
A laundry room is where people usually put food for pets. That's our
Eh, I do put my
Yeah.
cat food in my
Yeah,
laundry
it's
room,
like
but
in a
when the cat
cabinet.
gets in there, he bites into it, breaks it open, wrecks it, so. Keep the cat out of the laundry room. All right, so here's another one that we're gonna be looking at, making observations. These are, tracks of animals in the snow, right? So we have a bobcat and a hare. So, what observations can you make?
The
Bobcat
This
ate
is
the
the
hare.
bobcat, this is the hare.
The
Bobcat
bobcat
ate
ate
the
the
hare.
hare.
Yeah, but that's an inference, right?
Dinner.
Our observations are there are two sets of footprints, bobcats and a hare,
Snow.
and then there's
Go
no
walked in.
more.
It looks like it's snowing.
Looks like a little altercation may have happened right there. Yeah, I don't see any blood or anything, so I
They
don't know.
swallowed it whole.
Yeah. I mean, who knows? Maybe the rabbit's hole's just right under there.
It looks like
And he
it
ran
looks-
away, got away. Let's be optimistic for the poor bunny.
It looks like snow.
I think it is in the snow.
Maybe
Yeah.
he played dead.
Yeah,
I
but
think
there's,
he's-
I think the bobcat would still take a dead
Yeah.
one. Yeah. But maybe he ran through a hole. I don't know.
The bears won't easily get fit.
All we know is that we had 2 sets at the beginning, and at the
Bears
end
are
there's
good,
only
good,
1
great
set
lives, so
left.
they're dead.
Okay, so that's an observation versus an inference. All right, here we go. We want to discuss a few. Let me move this out of here. I keep forgetting to do that. Okay, discuss scientific theories and laws, remembering science can't prove anything. Okay, can you think of a scientific theory that you've heard of and you wonder if it's true? Can you think of anything that science, some people may have said science has proven? You know, a really good one would say, well, okay, Olivia.
This is a dumb one, but gravity. People say they
Right,
believe
right.
in gravity.
What about gravity, right? Gravity works every time, doesn't it? Every time we try it, stuff falls down,
Let me
right?
jump off the table. Let's see.
Yeah, if you want to, if you jump, but then there are ways
Just
to
making sure.
bypass gravity. If we get far enough out in space, right? Or if we get on an airplane, we can bypass gravity. How about, something as simple as saying that COVID is caused by a virus?
That's
Right?
could be speculation.
Yeah, we think it is. We think it is. But we don't know for sure. If somebody tells you that this medicine I'm gonna give you will keep you from getting COVID, right? Maybe. We don't know. There's a vaccine out there that's supposed to keep from getting COVID, but there are people getting COVID
And 9.
after having a vaccine. So,
Why don't
so
they
we
put-
can't. It can't prove any. Science can't prove anything. Olivia,
I was gonna say, do you know if you get the vaccine, you have more of a chance of getting it?
are you asking if I know that?
Yeah.
We don't have enough data for that. We honestly do not have enough data for that. I don't believe the vaccine gives you the virus. I don't think there's enough virus in it. John Mark, did you have something?
Why don't they put the whole ingredients of the vaccine listed on it so you know what you're doing?
Okay. So John Mark's asking about what's in the vaccine. If we should be able to know that before we put it in our body, right? Now that it's been approved, we should be able to have that information. Now that it's been supposedly approved. I don't know.
What about those theories like Archimedes and like Newton made that some people that said they proved wrong?
Yeah. So if you might be thinking about like natural selection, spontaneous generation, where living things come out of non-living things, and for millions of years people believed it to be true, and millions of years, thousands of years people believed it to be true, and then somebody came along and said, and we were able to disprove it.
But we didn't know if it was.
Flies do not come from rotting meat. Flies come from mama flies.
I was about to say
Okay.
like a couple million years.
I meant to say thousand. Sorry, no million, not millions. Yeah, John Martin.
Wait, so if you are disproving something,
Uh-huh.
then that means you could have proved, but
No, that's the whole point. Some people might say they've proven something, but they're wrong, because science can't prove anything. All right, so they may have some strong evidence to support. We have lots of really strong evidence to support that gravity is real, right? We have a lot of evidence for that. But Newton came along and said the universal gravity meant that the force that's pulling stuff down to the Earth is the same force that's keeping the moon orbiting around the Earth. Okay, we're pretty sure he's right about that. In fact, those have been codified into something called the law of gravity, right? The law of universal gravity. And that means that we've tested it, and we've done things, we've tried to test it, and we have not been able to disprove it. But we can't officially say it's proven. Right here we're looking at some sort of chamber for subatomic particle experimentation. Okay, so subatomic means it's smaller than an atom, all right, which means it's a part of an atom, for instance, an electron, a proton, a neutron. These kind of things are being put into here, and we're testing. We're going to see in just a minute how there was a theory of what does an atom look like. The bottom line is we have no idea what an atom looks like, all right, but we have a good guess based on some work done by guys who went before us, previous things before us. All right, the main difference between a scientific theory, which we'll call an explanation, and a scientific law, which we'll call a description of something that has been shown over time to be true, is that scientific laws are supported by significant amounts of evidence that often include mathematical terms. All right, so there's lots of testing been done, lots of questions, lots of scrutiny. That means to really test and to see if the claim is true. Remember, not proven, but really good guess to establish it.
The theory of combustion.
Yeah, for the longest time, we did that in general sciences, that combustion was thought to be certain things contained something called phlogiston, and however much they had meant how well they could burn, but it turns out combustion's a chemical reaction, right? It doesn't have anything to do with it. Phlogiston's not a real thing. All right, useful simplification used to make it easier to understand things that might be too difficult to observe is called a scientific model. A scientific model. For instance, at the very beginning of this pandemic, there was a scientific model, not data. So the difference between a model is what might happen in the future. Data is what has happened and I've collected it. When this pandemic first began, we had no data, right? Because it was brand new. But we had these models, and one of the models said that like 100 million people were going to die from this, and we all panicked. Nobody wants 100 million people to die. And we went into the lockdown, and we went into all that stuff, all that crazy, the masking, all that stuff, right? Well, now we have a lot of data. It's a year and a half later. We have a lot of data. And the data shows us that the lockdowns and the masks are not as effective as we guessed they would have been. Our model was wrong. Furthermore, the model of the millions and millions was faulty from the beginning. So you can't always trust models. But one model that we count on a lot is called an atomic model. Like I said, we don't know what an atom looks like, all right? But we've made guesses over the years. All right, we're going to watch a little video here about the different guesses that have been made about what an atom looks like. So we have our Greek idea, and then morphing now into our, I don't know if I want to call it medieval time, into more modern times, into the most modern, the Schrödinger model right here. So keep in mind, each one of these is a model. That's because our skills of observation are not good enough to see these. Can y'all see okay? Do you need the light back on? Now that we're going to watch a video, we'll keep it off for now. I will tell you here that J.J. Thomson, one of my favorite guys out there, he did these really great studies on this. His is called the plum pudding model of the atom. In our video, though, they're going to call it the chocolate chip cookie model, okay? Because we don't know what plum pudding is, because we're Americans. He was British, and the British eat this stuff called plum pudding, I guess, and it's sort of like raisins suspended in pudding.
Ew.
Yeah. So
I hate British meals.
British meals, yeah, they're a little bit lacking in their, I don't know, taste. Yeah. British food's a little bland, I'll put it that way.
Yeah.
All right, let's watch a video about the idea of the model of the atom proceeding over the years.
What do an ancient Greek philosopher and a 19th century Quaker have in common with Nobel Prize-winning scientists? Although they are separated over 2,400 years of history, each of them contributed to answering the eternal question: what is stuff made of? It was around 440 BCE that Democritus first proposed that everything in the world was made up of tiny particles surrounded by empty space. And he even speculated that they vary in size and shape depending on the substance they compose. He called these particles atomos, Greek for indivisible. His ideas were opposed by the more popular philosophers of his day. Aristotle, for instance, disagreed completely, stating instead that matter was made of 4 elements: earth, wind, water, and fire. And most later scientists followed suit. Atoms would remain all but forgotten until 1808, when a Quaker teacher named John Dalton sought to challenge Aristotelian theory. Whereas Democritus's atomism had been purely theoretical, Dalton showed that common substances always broke down into the same elements in the same proportions. He concluded that the various compounds were combinations of atoms of different elements, each of a particular size and mass, that could neither be created nor destroyed. Though he received many honors for his work, as a Quaker, Dalton lived modestly until the end of his days. Atomic theory was now accepted by the scientific community, but the next major advancement would not come until nearly a century later, with the physicist J.J. Thomson's 1897 discovery of the electron. In what we might call the chocolate chip cookie model of the atom, he showed atoms as uniformly packed spheres of positive matter, filled with negatively charged electrons. Thomson won a Nobel Prize in 1906 for his electron discovery, but his model of the atom didn't stick around long. This was because he happened to have some pretty smart students, including a certain Ernest Rutherford, who would become known as the father of the nuclear age. While studying the effects of X-rays on gases, Rutherford decided to investigate atoms more closely by shooting small, positively charged alpha particles at a sheet of gold foil. Under Thomson's model, the atom's thinly dispersed positive charge would not be enough to deflect the particles in any one place. The effect would have been like a bunch of tennis balls punching through a thin paper screen. But while most of the particles did pass through, some bounced right back, suggesting that the foil was more like a thick net with a very large mesh. Rutherford concluded that atoms consisted largely of empty space, with just a few electrons, while most of the mass was concentrated in the center, which he termed the nucleus. The alpha particles passed through the gaps, but bounced back from the dense, positively charged nucleus. But the atomic theory wasn't complete just yet. In 1913, another of Thomson's students by the name of Niels Bohr expanded on Rutherford's nuclear model. Drawing on earlier work by Max Planck and Albert Einstein, he stipulated that electrons orbit the nucleus at fixed energies and distances, able to jump from one level to another, but not to exist in the space between. Bohr's planetary model took center stage, but soon it too encountered some complications. Experiments had shown that rather than simply being discrete particles, electrons simultaneously behaved like waves, not being confined to a particular point in space. And in formulating his famous uncertainty principle, Werner Heisenberg showed it was impossible to determine both the exact position and speed of electrons as they moved around an atom. The idea that electrons cannot be pinpointed but exist within a range of possible locations gave rise to the current quantum model of the atom. A fascinating theory with a whole new set of complexities whose implications have yet to be fully grasped.
You don't understand.
Even though our understanding of atoms keeps changing, the basic fact of atoms remains. So let's celebrate the triumph of atomic theory with some fireworks. As electrons circling an atom shift between energy levels, they absorb or release energy in the form of specific wavelengths of light, resulting in all the marvelous colors we see. And we can imagine Democritus watching from somewhere, satisfied that over 2 millennia later, he turned out to have been right all along.
So, if you did general science, Democritus was the one who had the idea, when you're looking at the beach, it looks like a yellow blanket, and then you get closer and closer, you see those little grains of sand. So he's that guy. So he ended up being correct about that. Maybe not correct in every aspect of it, right? But correct in the idea that things are broken down into smaller things. Now Dalton comes along and he says, you can't break them down any further, but it turns out there are subatomic particles. In fact, chemistry is all about taking those electrons and making them react with other electrons. So we're literally taking electrons off of atoms and using those. In fact, when you have static electricity, you have a little spark or whatever, that's just free electrons that are just roaming around. So Dalton was wrong. J.J. Thomson was wrong. And so, but he took another step to bring us closer and closer to what we think is. So truth is, right now, the way an atom looks, we're probably wrong too, right now. We typically use the Bohr model. That's where we have a nucleus with things spinning around it because it's easiest to picture it that way, even though we know it's not exactly true. It's okay, it's still useful. All right, so I'm hoping when we get to heaven, we'll have a really, really super duper strong, microscope that we can all see what an atom actually looks like. Most people say you probably won't care. Probably not, but I just am so interested in this stuff that I'd like to know what it really looks like. Yes.
Isn't it Japanese like fireworks?
Chinese.
Oh, Chinese.
Yeah, the Chinese invented fireworks.
What was it for?
Well, they accidentally discovered it. It was accidental at first, but then they realized they could send messages. So they came up with like little rockets they sent up, and the rocket would blow up and it would send a message. If they sent 2, it meant yes. If they sent 1, something like that. Then they realized later they could use it for weaponry. So bombs and things like that. Yeah.
Imagine getting bombed by a
And then we
firework.
started using it for celebrating things.
And then celebrating things. So I will tell you the vast majority of the fireworks we have on July 4th are made in China, sadly. Okay,
A lot of them are made in America though.
are they?
Yeah.
You sure?
I bought some that were made in America.
It said Make America on it? Very nice. How we measure and use data is important for scientific analysis. We will use the metric system in this class, okay? We will not use the English system, which is unfortunate that I forgot to bring my little ruler because my tape measure is in the English system. Meaning today we're going to measure certain things with inches instead of centimeters. I guess we could look it
Yay.
up online and convert it over or something like that. All right, so the base unit for these things, for instance, if we're going to be measuring the length of something, we're going to be using something called a meter. And a meter stick. I have one of those too. I was supposed to bring that, but they're kind of long and, you know,
Where
wouldn't.
the fun of actually.
If I'm using an English unit, that would be feet. And that's what we're more familiar with as Americans. We still use the English system in America. We're one of the only countries in the world that does. If you drive into Canada, you'll see things that talk about how many kilometers per mile you can drive, and we all sit there and go, oh, what does that mean? So mass, we'll be using the gram or the kilogram. A kilogram is just 1,000 grams. 1 gram is about the weight of a housefly. So that's why kilograms we'd want, like, you know, so we can measure bigger things. We're going to be looking at gram scales today and putting some different weights on there so we can see how they compare. So we use a kilogram or a gram. Here we have kg as the symbol. The corresponding English unit, by the way, is called a slug. Has anybody ever heard of a slug when talking about measurements? I have because of, you know, science class, but I've never actually measured anything with a slug. So I've never weighed anything with a slug. The slug is a little, you know, snail without a shell, you know, in your garden, right? Bad news. So I don't know that we ever really use that. Fortunately for both the metric and English, time is measured in seconds. Nobody else has a different time scale, so we're okay on that one.
Yes.
And if y'all need more light, I can. Sorry.
No.
Are you okay with it all?
Yeah.
No, you
Yeah.
prefer it off? Okay, so quantitative observations usually involve measurements, and so today we're going to do some quantitative measurements and qualitative, and comparing a couple of things in the little lab that we have to do today. So we'll be looking at length, mass, I don't know if we'll do volume, and then time, if it takes time for something to happen to these things we're looking at, okay? All right, common prefixes used with SI units. SI would be the metric units right here. So if we have this number is a trillion, we use that prefix, which is it Torah or Tera? Can y'all see it? We don't use that one very, it's Tera, T-E-R-A. Mostly we use giga. You've heard of a gigabyte, a megabyte, that kind of thing. 1,000 is kilo, kilometer, kilogram. 100 would be hecto, 10 would be deca. A tenth, that's a tenth, which means 0.1 is deci, like a decimeter. Centimeter, you probably heard of a centimeter, that's 1/100th, 0.01. My poor chemistry kids had a quiz on this stuff today, and they had to tell me what a centi was. It was 0.01. A thousandth would be a millimeter, or a milligram, or a milliliter. That's a 0.001, which is a thousandth of one, right? A millionth, a billionth, and a trillionth. We rarely use those. Is that micro, nano, and pico? I guess nano and pico are used in things like computer type sciences right there.
You know what's convenient?
Hmm.
We were going over place value in my math class today.
Oh, sure enough, there you go. Do y'all do like a scientific notation and stuff like that?
I don't think so.
Where you move that,
Or
you don't-
algebra.
no? You move the decimal point and count
Oh.
times 10 to the
yeah.
something power.
Just
Yeah, it's called scientific notation. We use that in chemistry a lot. I don't know that, we'll be talking about chemistry in this
yay.
class, so. Yeah.
So fun.
Yeah, physical science does include math, so it's kind of a bummer because you have math class for that. So what are y'all filling in?
The chart.
Okay. Can you see it well enough?
Some of the L's look like S's, but
Yeah, it looks kind of blurry up on the,
Hold up.
I think on the screen it looks pretty good. Those who are watching the recording should be able to see it pretty
Oh,
clearly. It's just the projection that is a little blurry. Let me see if I can make it. Y'all tell me if it looks
I
better.
got
that's
Phyllis
you.
and I can't
Oh,
figure out why.
I
Better?
was like, hold on a minute. What
A
am
little
I missing?
better?
Because on the unit
Yeah.
one, it's like split up and there's no name for the unit. So I was like, hold on.
Here, the unit, 10th, 100th, 1000th.
Trillion.
That's small, yeah.
Pico sounds like a Spanish name.
Pico de Gallo. Doesn't it just mean little?
So,
I don't know what it means in Pico de Gallo, but
Livia, what does it mean?
Pico de gallo?
it's salsa, right?
No, it means jalapenos. It's
Are they cut tiny? Are they cut small? Maybe pico
Yeah.
means small cut up or
pico
something.
means spicy.
Oh, it means spicy.
It is if we add jalapenos in it.
Done.
Yes, how's it coming? Are we good? Y'all have to fill in every one of the boxes?
Yeah.
That's a lot of writing.
No, every other one.
No, that's what I
Oh, every
have.
other
That's what I have math for. That's what I
Got it
write.
wrong.
We write a lot in math.
Yeah.
It's less writing than we did with Miss Lou's stuff. So. We have a
Yeah,
lot
you
of
have to
writing.
you have to do your math problems right there in class, right? Yeah. How exciting. Nothing against math.
I'm telling you.
I just prefer science. I wish I had a math mind, I really do.
My
I
mom,
know.
she's not really good at math. My dad is though. He's like super good at it. He doesn't get like all the kind of new math they have today. But
New math,
it's like he
2
just,
plus 2 is 4.
he said it's different than what they had, like all the different techniques. they
Yeah.
have.
Everything's getting new stuff.
When is
Science
that?
book, math.
I was gonna say
My
when you
dad
say
literally
math
just
is
turned
new,
40.
I was
He's
like,
old.
How old?
40.
Oh my goodness.
My mom's 36.
My daughter just turned 35, so that tells you how old I am. Alright, we good?
Older than my
No.
Are you older than my
No.
dad then?
Oh yeah, I'm a grandma.
Oh. So she.
I'm the age of your grandma.
So's my mom.
Your mom's a grandma? Do
Uh-huh.
we need this back, people?
Yes.
Nope.
no, I'm good.
You can talk. No.
Are we good? No, Mark, you still working on it?
She can copy someone else's paper.
Okay. So prefixes, we have T for trillion, M for million, K for thousand. Oh, look here. Were y'all supposed to fill this in? Is that what you have in your book?
No,
Yeah.
unit is like.
Oh, okay. So you had to fill these things in.
Yeah, that's what we did.
All right, there you
Fill in
go.
all the blank spaces.
All right. Well, good. I thought maybe I was supposed to fill this in for you.
Yeah.
I didn't fill that in for you. Okay. All right. So when we're looking at measurements and measuring things and being very exact about the way we measure things, we have this story of the lost spacecraft due to a metric math mistake. Okay, so in the 1990s, 98 I think, NASA was sending the Mars Climate Orbiter up to Mars. It was going to be our first time to have something visit the planet of Mars. And here's what it looked like.
Oh, nice.
And it turns out when they blasted it off and they sent it off, they lost track of it and went floating off into space, and the millions and millions of dollars were never seen again.
Like
They
what direction?
never found it?
No, it's gone. Phew,
What
out of
direction?
the outer
What,
space.
towards what planet?
Well, what happened was that the measurements that were taken by one of the groups called Lockheed Martin, is that right? I think it's Lockheed Martin, who makes airplanes, right? They had used the English system of measuring, whereas NASA had used the metric, and nobody wrote down the actual units. So something would have said 25, and you're like, oh yeah, 25 feet. And they meant, no, 25 meters. And because it was wrong, instead of having the trajectory that was going to put it into the orbit around Mars, it put it into a trajectory that sent it slingshotting around Mars and out into outer space.
Did does it
Was there
like,
someone in it?
No.
did it go towards like a direction towards another planet, or did it?
I don't, it's gone.
Maybe it's already on another planet.
Well, we don't have any information from it. We have no data being
Maybe
retrieved from
like-
it. Anyway, it was a huge
Oh, there it
mistake.
is.
And so they figured out their mistake, and they said, well, that was a bummer that we did that. So they sent out a new one. Is there a year on this one?
Wasn't that recently?
1999
99?
or 90 something. I can barely read.
Something.
January something
Oh, I can't even read it on there.
99.
What? Are you reading down here?
Oh,
No,
it's
no,
on
it says
First,
launch. It says January
1999.
1st, 1999.
Oh, I see that.
Okay.
Yeah.
Eyeglasses.
All right, anyway, we corrected the problem. We sent a probe up to Mars. It was pretty cool stuff, and they had this really fancy way of dropping it down. And it was successful, started sending data back to us. And so since that time, we've been collecting data from Mars. We have found no evidence whatsoever of any life on Mars, but we would like to see about getting humans to Mars. So that's one of the steps to get us there. All right, so what is NASA up to right now? Now, NASA is the U.S. version of the space program, right? And so therefore it's being funded by our government. And because that's the case, the government gets to tell it what to do. And because presidents change from one to another, one president said, let's go to Mars. The next president says, no, we don't want to go to Mars. The next president, yes, we want to go to Mars. So now we're kind of in the yes, let's go to Mars kind of routine because the new president hasn't made a decision whether or not he thinks we should spend money on Mars. So let's see what we're up to.
3, 2, 1, 0. Mission liftoff.
Artemis 1 will lift off from Launch Pad 39B at NASA's Kennedy Space Center in Florida with 8.8 million pounds of thrust provided by the most powerful rocket in the world, our Space Launch System rocket, or SLS. The uncrewed flight will be the first integrated test of SLS, our new Orion spacecraft, and exploration ground systems at Kennedy. Artemis 1 will send Orion beyond the moon, 280,000 miles from Earth, farther than any human spacecraft has ever flown.
This is not NASA doing this. This is the United States of America doing this program, the Artemis program, and there are companies all across our country that have a part in it, so there is kind of this wave of excitement being generated just by saying, we're going back to the moon.
After the upper stage of the rocket separates from Orion, the upper stage will deploy small satellites over several days to perform science experiments and technology demonstrations. Orion will make its multi-day outbound trip to the moon, propelled by a service module provided by the European Space Agency. Engineers will test Orion's systems on the way to the moon. Then, Orion will fly about 60 miles above the lunar surface, using the moon's gravity and engines on the surface module to enter a lunar orbit. After about a month and a total distance of over 1 million miles, Orion will return home, faster and hotter than any spacecraft has before. A primary goal of Artemis 1, ensure Orion safely returns to Earth before we fly with humans. When we do, we'll build our capability for sustainable lunar exploration, preparing us for missions farther into the solar system.
Initially, what we'd like to do is start establishing a presence on the moon. So we're going to establish going back there on a regular basis, and then we'll end up setting up Gateway, and we would launch to the Gateway, and from Gateway, land on the surface of the moon.
We are there for, weeks, months on end. And there, we're going to be able to test out all the hardware, the habitats, and the hatches, and the suits, and the rovers that'll allow us to prove out those technologies. The moon will lead the way to Mars, and we should be there within the next couple decades.
They could just jump off Mars and just go to like launch off the moon and go to Mars.
Well, they want to set up like a base on the moon, and then we can leave from the moon to get to Mars. Then we don't have to worry about getting out of Earth's orbit to do that. Okay, so we're going to make some observations. What we have here, this is straight out of your textbook. All right, so I have some things for you. And what we're going to be doing is we're going to be using
Miss Pastor, is this experiment 1 or 2?
I guess it's 2 technically.
That's like 2.
So I have 2.
I've been stressing out so much.
And what happened?
How different is the reading of chapter 1
the
in our textbooks other than the
I
old
better not
textbook?
have the recruits.
How different it is from the old textbook?
Yeah, the reading. Like reading
Very different. Pretty sure it's like totally different. Do you have the old book?
Yeah, I was reading it this week.
Did it seem like anything we talked about studying from there? I know.
I guess I'll see that.
You're getting the new book though, yeah? Okay.
What is this experiment called?
This is called Making Observations. Making Observations, yeah.
How
So
do
I'm
you-
gonna give you an eraser. Okay, some of you have a big eraser, some of you have this kind of eraser.
How do you win an Earth prize? Are you too super
Oh,
smart? or-
yeah, we had to come up with something so earth-shatteringly different than other things. For instance, finish this let me cut off this video right here. Okay, we're gonna do the lab now, and we're gonna do this experiment. You can do this one at home probably, for those of you who are listening in. I'm gonna turn that off.